Hello everybody, welcome to Organic 1 lecture for the McMurray textbook. This is chapter 12. I'm talking about structure determination, where we utilize mass spectrometry and or infrared spectroscopy. All right, and so this will be a two-part series for this chapter. The first part will go over mass spec, and then we'll go over IR in the second part. So jumping right in with mass spec. There's a bunch of stuff here, but really what we want to be able to do is interpret mass spectra. We'll talk about some common functional groups, and we won't really worry about the time of flight stuff for biological, but we are looking typically for organic chemistry, we are looking at small molecule determination. We can get kind of a glimpse of structure, but later on in chapter 13 or in a different chapter, we'll be talking about NMR, and then that's going to be a little more informative, right? And of course, the IR objectives will be in the second video. All right. For mass spectrometry, your general layout for a mass spectrometer, where you have some type of ionization source where your sample goes in, and it can get heated and ionized, and then those ions will fly through some type of path, but that path is affected by a magnet, right? And so these ions have different masses, so therefore they have different weights, so to speak. But they're also charged, so they will actually feel this magnet. So the fragment based off of its charge and its mass will have its path deviated once it feels the presence of this magnet. And so that's what's kind of utilized here in getting a bunch of different fragments or peaks in your mass spectrum. All right, so just generically here, the sample is vaporized at the ionization source. So it's vaporized, and we see it turn into cationic radicals. And so just kind of like looking at it from, say, a reaction standpoint, you'll have an organic molecule. It'll get ionized by in the process of getting ionized here. That's what this red electron arrow is showing. Right, the first thing you will typically see is that you form this cationic radical. So it has both a positive charge and it is a radical. And so at this point, the molecule hasn't actually broken apart. It's still intact. So all of the atoms are still on the original molecule. And then as you create this cationic radical, this will start to rapidly break apart into a bunch of different pieces or fragments. Right, and those fragments will pass through that magnetic field, and we will see the different fragments separated based off their mass and their charge, or aka their mass to charge ratio. And so you're going to see it on the mass spectrum as MZ, mass to charge ratio. All right. All right. There are different types of analyzers. One of these is a quadrupole. I'm not really going to go over that in any great detail, but a simple mass spectrum that you will see here, you can see here that you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. For this molecule, you have 15 peaks. All right, but do you notice the arrows are pointing to really like one peak, to one peak within the cluster? So you have the tallest peak in this cluster that's being identified, and then the tallest peak in this cluster that's being identified. Now, this is a very small molecule, right? So this is what we call the parent peak, or the M plus peak. So parent or molecular ion peak. And this really is just your molecule before it's broken apart. So it's going back to that original reaction that we saw here. So when you see an M plus peak, it's really just saying your organic molecule was ionized. So it's a cationic radical. All right. And then if you look here, this tall peak that is 100% abundance, this is what's called a base peak. Right. These two terminologies are very important. Two terms are important for you to pay attention to here. Base peak and your parent / molecular ion peak. Now, with this, you can actually if we know one particular thing here for this molecule, if we knew that this molecule was composed entirely of carbons and hydrogens, right, we can actually kind of come up with 1, 2, 3 possibilities in terms of what our molecule is. And so if we look, we know it only has carbons, a certain number of carbons, and a certain number of hydrogens. So you can actually, knowing this only carbons and hydrogens, and it is, you can estimate the molecular formula, and from there even maybe make estimations or hypothesize what the structure is. So what I would recommend is you look at the carbon and the hydrogen, right? So this is a mass to charge ratio, and all of these charges are understood to be +1. So the Z here is always 1. So you're saying your mass divided by 1, which gives you just your mass, right? So if this is understood to be a +1 charge, then to get a mass of 44 here, how many carbons could fit into that? Well, you know that each carbon is approximately 12 AMU, right? 12.01. And you know that each hydrogen is 1 AMU. So how many times will 12 go into 44? Well, let's see. If it were C3, that would say 3 times 12, which equals 36. So you're still under the 44, okay? If you said C4, that would be 4 times 12, which would be 48. Well, that's too big, right? So we automatically know that there can't be 4 carbons, right? And lastly, let's look at C2. That would be 2 times 12. That equals 24. So really, let's just say from here, the way I do this is when I'm trying to estimate, I'll go, okay, so what I'll do is I'll look at the number of carbons until I get a failure, like I did here. And so I did C3 first. I said, okay, that one passed, but the next bigger one failed. So let me go down 1. So instead of C3, I did C2 to see the mass there. All right, so I just said, okay, I got 2 options here. I either have C2 or C3. Well, my total mass has to be 44. So for C3, HY, right, that has to equal 44. So really, I just say 44 minus 36, which would have been 8. So C3H8 would give me a mass of 44. If I look here at C2, right, C2HY equaling 44, that would be, well, 24. 44 minus 24, oh, C2H20 would give me a mass of 44. Is there any way that I can have 20 hydrogens when only 2 carbons are present? No, right? Each carbon can only have a maximum of 4 bonds. So even if you just looked at these carbons isolated, right, you would say 2 times 4 would be 8. Right? So yeah, you can't do that. So goodbye. Right? So C2's out. So really, we're looking at C3H8. Right? Now, we can make further estimations. So for C3H8 equaling 44, right, something I can do, which we haven't really talked about yet, but we can do something called the degree of unsaturation for carbons, which the formula follows 2 times the number of carbons plus 2 minus the number of hydrogens, all divided by 2. And so really I would be saying 2 times 3, right, because C3H8, so 2 times 3 plus 2 minus 8. So 2 times 3 plus 2 minus 8, all divided by 2. So what does that give me? That gives me 6. That gives me 8 minus 8, so it gives me 0 over 2 equals 0. So this has a DOU of 0, which means, based off the number I get here, that tells me how many pi bonds and or how many rings are present. So with a DOU of 0, that means no rings, no pi bonds, right? And so from there I can actually estimate for what can I get for C3H8? I'd get something like a 3-carbon chain. And really there's no other constitutional isomer for this. Yeah, there's no other constitutional isomer. So this was actually for propane. And I'm going to feel really dumb if it says it in here somewhere. Yeah, okay, so this is actually the mass spectrum for propane. All right. And I went ahead and showed you all this because this is something that you can do in the future, and for those of you in lab, this will be very helpful. All right. Now, some other things that I stopped here, but I didn't even look at the base peak. But when you start to get a bunch of different constitutional isomers, that's when these other peaks are going to come in handy. And so, like for this, really you want to think about if this is your parent, well, your next logical fragment would be cutting a carbon-carbon single bond. So you would cut this, and hang on. So if that's the plus dot, right? You would cut this, and you would get two fragments. You would get CH3, CH2, and then you get CH3 over here. One of these would get the plus charge, the other would get the radical dot. And for right now, I'm not going to worry about that. But if you look at these two, this has a mass of 29 mZ, and this has 15. Right? How did I do that? All right, same thing I did up here, right? Two carbons, so that's 2 times 12, that's 24. 24 plus 3 is 27. 27 plus 2 is 29, right? So 29. So my base peak is actually due to an ethyl fragment. All right, and you can sometimes follow that, but there are other instances where we'll have to deviate slightly. So, as you saw me do previously, we got the molecular weight from the parent peak, right? The M plus peak. Right, and really what we see happening, every compound has its own molecular fingerprint in terms of its mass spectrum, like how it breaks apart, and we see a lot of predictability in how certain structures will break apart. For instance, the predictability in, say, if we had this molecule right here, in terms of naming it, we have 1, 2, 3, so we have propane, right? So that is 2,2-dimethyl. So we have 2,2-dimethylpropane. Now, the way it will break is characteristic in terms of when you start with your molecular ion peak, or your parent peak here, or your parent fragment, nothing has actually cleaved or cut. No bonds have broken. You've kind of just done something with an electron. Now, what we see here is a lot of times we cut a carbon-carbon single bond, and in cutting one of these, this is actually very good because when we cut here, we have to do the cut because this is going on in a mass spectrometer. And the fact that it's a radical and a positive charge, it's very unstable. So it's actually breaking these bonds to try and become more stable. Now, what we see happening here, you notice this carbon here got the plus charge and not this one. And that's because if you look, this is called a carbocation, a carbon with a positive charge. Carbocation, all right, a carbon with a positive charge. And so when we look, this carbon has 1, 2, 3 other carbons attached to it. So this is actually a tertiary carbocation, which makes it a relatively stable, a pretty stable carbocation. And so, but if you were to go to this one, and if you were to say, oh, that's the ion that I would see at 15, no, because this is a methyl carbocation. That's very unstable. So carbocation stability pretty much goes in the realm of you have CH3 plus is less stable than a primary carbocation, right? This carbon has a positive charge. It's only attached to one other carbon. Then a secondary carbocation is more stable than that, and then a tertiary carbocation is more stable than a secondary. So you have methyl, primary, secondary, tertiary. Tertiary carbocations being the most stable. Okay, so that's one thing to think about as these structures break apart, right? Which structure gets the positive charge? Well, in this case, these are nothing but alkyl fragments, so nothing but carbons and hydrogens, no double bonds, nothing but single bonds. So when you look at this, right, which one would have gotten the positive charge? Well, you're looking at a tertiary carbocation versus a methyl. Tertiary is more stable. So that's the fragment we're going to see. Okay, this fragment is invisible because it doesn't have a charge, right? So in this case, Z equals 0, right? There's no charge. It's neutral. So the mass spectrum won't actually see this fragment. Okay, it has to have a charge. All right. And so, like I said before, we do see some predictability here in terms of how fragments will break apart. For here we have hexane, right? So you start with 2, 3, 4, 5, 6. Right? So hexane is C6H what? That's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, H14. That gives you a total mass of 86. So the 86 peak is definitely your parent peak, right? That's your hexane before anything's broken off. And then if you look here, right, these have been pointed out to you, but you notice the same trend. You have a cluster here, you have a cluster here, a cluster here, and a cluster there. So you have 1, 2, 3, 4 clusters of peaks, and the tallest one of each cluster has been identified, has been paid attention to. And so when you look at 57, right, that is also the base peak, but when you look at 57 here, right, this is the tallest of this particular cluster. And so how do we get 57, right? Well, you're cutting stuff off. But something that's really easy to do is to say, well, what's 86 minus 57, right? What's the mass difference there? And I'm going to cheat. I'm going to pull up a calculator here and let you see the calculations I'm putting in. Wait, where'd it go? It disappeared. Alright, anyway. So we're going to say 86 minus 57. Right, that's a mass of 29. Well, we actually just talked about this a second ago. Right, this mass difference is an ethyl. So equals 29. So that tells me that an CH2CH3 or an ethyl mass came off. Alright, so to go from 2, 3, 4, 5, 6, right, which is 86 to 57, that means that a CH3CH2 had to have been cut off. So what I'm going to see here is 1, 2, 3, 4, 2, 3, 4. I'm going to see that as my, oh, you can't see it. I'm going to see that as my 57 fragment. Right, and I can keep doing the same thing with the rest of these, right? I go from 57 to 43. What's the mass difference here? Right, 57 to 43. That looks like a 14, right? Well, if I go back over here, right, if I'm starting at 57, because that's the mass difference I chose, 2, 3, 4, right, to 43, so 57, and I need 43. Well, a mass difference of 14, what is this carbon at the end? That's a CH2, right? Because it was this carbon, right? And that's a CH2. So if I cut this, that tells me that I have a 3-carbon chain with a plus charge now. Okay, so I cut off, I just said minus CH2. I cut off a CH2. I said minus CH2, CH3. I broke off an ethyl. All right, and you can kind of repeat this process for all of them. All right, now if it's just an alkyl chain, it's usually something as simple as just start cutting some carbon-carbon single bonds. Now, when you have different functional groups like alcohols or amines, we see other predictable fragmentation patterns emerge. So both alcohols and amines undergo what's called an alpha cleavage. All right, so we have to think about what does that alpha mean. Okay, so in this case, you notice for the alpha cleavage, what it's saying is, look at your alcohol functional group, right? There's the carbon it's attached to. That's ground zero carbon. And if you take one step in either direction, let's say that's a carbon, and let's say that's a carbon. This structure has 3 alpha carbons, right? 1, 2, 3. And what they did was they just picked one of them to cut off, right? So they did an alpha cleavage and they cut off this alpha carbon. Okay, so that's why you see RCH2 here. And then this carbon, because this is the bond that you broke, this carbon gets the positive charge. Now, this alpha cleavage is favorable because what you see happening here is a resonance structure emerging. So having resonance makes this fragment stable or slightly stable. All right, and you can see the same thing happening here with amines, right? Look at the nitrogen of the amine functional group. There's the carbon. That's ground zero. And if you look, this is one step away from ground zero carbon, so that's an alpha carbon. So it cuts it off. You see that the fragment that we got, the carbon that's had the amine attached to it, the NH or NR2, right, it gets the positive charge, and yet again we have the possibility of a resonance structure, so adding some stabilization here. Okay, so that's why alpha cleavage is for alcohols and amines, and we're going to see carbonyls too. That's why they are stable, because you have this resonance structure in the fragment, in the positive fragment. Now, the other thing you can see quite frequently with alcohols is what's called a dehydration. Dehydrate, so you lose water, right? And that's why you see water as a product over here. In essence, what you're going to see is the alcohol, the OH, is going to leave, and then an alpha hydrogen is going to go. So the big thing here is this has an alpha hydrogen. That's the alpha carbon. Now, what's going to happen if, let's say, if you look at this structure, right? So these are the two alpha carbons. But what if you have this type of scenario, right? These are methyl groups now. So both of these alpha carbons do not have hydrogen, so it cannot do a dehydration. Okay, but as long as there's an alpha hydrogen present, you can see this dehydration as a possibility. Okay, as a strong possibility. And you notice in the dehydration, this acts a little bit like what we call an elimination reaction, where you see a single bond between the two carbons and you end with an alkene, a double bond. All right, so in essence, one way you can think about this is kind of a internal reaction, right? One of the lone pairs on the oxygen takes the hydrogen. It therefore breaks this carbon-hydrogen bond and donates those two electrons between the carbons, which then allows the oxygen to be kicked off. So you see all three of these things happening within the same molecule, all three electron movements. Okay. All right. Now, as I said before, carbonyls can also experience that alpha cleavage. Where's my carbonyls? Right, carbonyls can also experience that alpha cleavage, right? So in this case now, the carbonyl carbon, right, that's ground zero, right? So this is zero. So this would be the alpha positions, the alpha carbon positions. And that's why you see this being cut off, right? And so if that got cut off, that's why it's now the radical there. And you get a plus charge on the carbonyl carbon. And as I said before, with the alcohol and the amine, you have this resonance possibility, and so you can move the plus charge off the carbon to the oxygen, so imparting a little stability. All right, now the other thing with carbonyl compounds, oxygens always tend to be a little more complicated when they're present, but the other thing you can see with carbonyl compounds is what's called a McLafferty rearrangement. Okay, so rearrangements are always internal. Okay, now in this McLafferty rearrangement, what winds up happening, I don't like the way this shows the arrows, but what you see happening here, you have a carbonyl and you have an alpha, beta, gamma. So you have a gamma carbon that has a hydrogen on it. So you have to have gamma hydrogens. Okay, so like I said before, for the dehydrations, you have to have alpha hydrogens. For the McLaffertys, you got to have gamma hydrogens. So look at the carbon 3 steps away. 1, 2, 3. Alpha. So that's the alpha carbon. That's the beta carbon, gamma carbon. All right, so you got to have gamma hydrogens. And in essence, I don't really like how this does it. Let me just redraw it. Okay, so I'm going to give you a specific example like this. All right, so if you look alpha, beta, gamma, so you have a gamma carbon, and I'm going to draw the hydrogen on it. Okay, so what you see happening for this rearrangement, this internal mechanism, lone pair on the oxygen takes the hydrogen. Hydrogen cannot have more than one bond, so the carbon-hydrogen bond has to break, donating electrons between these two carbons, right? It has to move back towards the carbonyl, okay? Because in essence, in forming this bond, we make the oxygen a positive charge, right? And so it's not going to be happy, so we need to somehow alleviate this, and so we're donating electrons this way. Well, we can't just stop there, because the problem that arises here now is this carbon will have too many bonds, right? It's got 1, 2, 3, 4 already shown, and with this pi bond here, you're putting a 5th bond on the carbon, and it can't do that. So now this bond has to break. All right, so this carbon-carbon bond has to break, donating between these two carbons, and then thereby pushing that pi bond up to the oxygen. So if I label these as alpha, beta, gamma, maybe it'll make sense. So this becomes a single bond. So you're going to see hydrogen, carbon, oxygen. All right. So this carbon-oxygen bond becomes a single bond. It grabbed a hydrogen, so it's now an OH. All right. And if you notice, carbonyl carbon and the alpha carbon has 2 bonds now. Boom, boom. And that alpha carbon had 2 hydrogens on it already. This bond right here, the alpha-beta bond, breaks. Okay, so now you're going to get beta and gamma. Did I write? I wrote alpha. Sorry. You're going to get beta and gamma, which I'll label them beta and gamma. Right. They're going to now have two bonds between them. The beta, I showed the two hydrogens on it. All right, like so. And there you go. Those are the two products you get. You get an alcohol fragment, and you get an alkene fragment from that McLafferty. All right. Now, I am going a little bit out of order, but that's okay. All right, something else we want to look at in terms of functional groups, common things that happen. If you have what's called allylic carbocations, or if you can form allylic carbocations, those are good. So in terms of what does this allylic thing mean, you have a carbon-carbon double bond, and then one of those carbons has a single bond with another carbon. So that right there is the allylic carbon. Okay. Now, what we see happening in the ionization, in essence, is that you are going to see this bond preferentially break, right? The allylic carbon and the rest of the chain is going to break off. And in doing it the way I'm showing it here, that this carbon gets a positive charge. And that's okay, because this does have the possibility of a resonance structure, right, like so, where this other carbon becomes positive. So you notice a recurring theme here. Resonance is key. All right. Now you can have the same thing happen instead of a pi bond if you have a lone pair. And so if you notice what happens here, you treat this like a double bond, like we did up here. So you, well, no, sorry, don't do that. So if you were to break this right here, right, you'll get a plus charge there, right, which is this structure right here. Now the great thing is you have a plus carbon bound to an atom with a lone pair. Well, just like we saw with like the alpha cleavages, so this is like an alpha cleavage, just like we saw with the alpha cleavages in alcohols and amines, all right, we get that resonance structure due to the lone pair, and it's more stable. The other thing that's very common to see, anytime you see a 77 mass fragment, that's kind of a big indicator that you have a benzene ring. So you've got something like this with a positive charge somewhere around it. Okay, so yeah, 77 is very distinctive for that functional group, a benzene ring functional group. At for bromine and chlorine, bromine and chlorine has two major isotopes. They have an M and then an M+2 isotope. Okay, so you're gonna see these see at 64 and then an M+2. So that's actually at 66, right? And so those are two very prominent peaks, right? We're not talking about this one at 65. We're talking about this one at 66. All right, so one thing that will stand out whenever you have bromine or chlorine is having this M or M+2 set of peaks. Okay, the ratio, how tall the two peaks are relative to one another, that's going to tell you which halide you have. So in this case, you know, this is chlorine because it is a 3-to-1 ratio. This peak is 3 times taller than this one. If it's bromine, it's going to be more of a 1-to-1 ratio. So they both would have been about the same height, you know, something like that, right? They might not be exactly the same height, but they'll be really close. Like maybe if they were both that height, right? That could be how similar they are in height. This isn't bromine, all right? Don't misunderstand what I'm trying to do here. But the bromine one would be about that height. Okay. And then the rest of this has an example of how you can see fragmentation. And in this case, you have an ether functional group. And the big thing to remember here is you have that lone pair on that oxygen. So one of the prominent fragments that you're going to see is going to follow this lone pair electron resonance structure. Okay, so and there is all of these shown. I do recommend that you go through and from the slides try and figure out these different fragmentations, how they happen. All right, so that does it for mass spec. Next up will be IR.